Pluto is a far-off and bewildering minor planet, once an individual from our planetary family. However, recent disturbing declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astounding revelation. They proposed that this chill world is on a collision course with Neptune. But how could this occur, and what may be the consequences of such a critical event? Are we seeing a charming, grandiose capriciousness? Or is there something else to this oncoming boundless impact? Join us as we research the possible results of a Pluto-Neptune impact. Pluto, a previous planet that was scaled back to a dwarf planet, is noteworthy because of its odd orbit, and it remains a subject of interest and study in the astronomical community. As shown by recent assumptions by leading experts, Pluto's orbit is perilously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous collision between these two planets, which would pose a significant risk to Earth. How is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our nearby solar system. It requires a complex 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even finished one full revolution yet. However, the interest doesn't stop there. Pluto's orbit is marked by its extraordinary bent shape, deviating significantly from the almost round orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination of 17 degrees to the ecliptic plane. The course Pluto follows is significantly steeper compared to other planets. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For at least 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we'd expect from their positions in the planetary system. This prompts the natural question: why hasn't Pluto slammed into Neptune? The answer lies in the gravitational impacts of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to determine its unique orbit. Unlike other planets, whose orbits lie close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and bent shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, despite these complexities, is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three bodies like Pluto, Neptune, and the Sun move and affect each other through their gravity. Pluto's orbit is, in fact, chaotic. Minor deviations in initial conditions can lead to significant differences over long periods. However, these surprising properties of Pluto's orbit have been found to maintain stability over particularly long timescales, keeping tumult in check. Recent simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Jupiter's immense gravity is strong enough to keep Pluto on a stable path for potentially billions of years. These factors are crucial in maintaining order and consistency in celestial mechanics. Without these factors, our solar system would be a place of far greater chaos and unpredictability. Pluto's orbit is a striking representation of celestial mechanics at play, showing both stability and turmoil within our local planetary system. The unique characteristics of its orbit, affected by the gravitational forces of nearby planets, particularly Neptune, highlight the complex and dynamic nature of space. Predicting significant events, especially when it involves chaotic orbits like Pluto's, presents tremendous challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainty. While mathematical simulations offer a solid means for understanding and predicting the future behavior of celestial bodies, they also highlight the limits of our predictive capabilities. So why are prominent astrophysicists only now raising concerns about a potential collision between Pluto and Neptune? Despite the various complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both renowned figures in cosmology, have expressed concern about a possible impact between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a captivating and catastrophic event in our solar system. The impact would release an enormous amount of energy, likely destroying Pluto due to its smaller size and icy composition. Debris from the impact could scatter across the solar system, possibly presenting a risk to other planets and their moons. For Neptune, such an impact could alter its current atmosphere and potentially its orbit, depending on the specifics of the crash. Michio Kaku, a prominent theoretical physicist known for his work in string theory, brings a unique perspective to the conversation. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics offer valuable insights into the mysteries of major phenomena like Pluto's orbit. Understanding the complex gravitational interactions and orbital mechanics of celestial bodies like Pluto can yield significant knowledge for future space missions. This information can help in navigating the solar system more effectively, predicting potential dangers, and even planning missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for how we might approach and understand distant worlds. In terms of planetary science, celestial mechanics and theoretical physics are deeply interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astronomy, offering a unique observational opportunity that might even connect to string theory. String theory, a theoretical framework where the point-like particles of particle physics are replaced by one-dimensional strings, aims to explain the fundamental forces and matter in the universe. The impact could create extreme conditions of energy and gravity, potentially leading to circumstances where predictions made by string theory could become observable. For instance, the high-energy impact could offer insights into the behavior of fundamental particles and forces under extreme conditions, a key area of interest in string theory. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific implication of such an event could be significant, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's mysterious dance around the Sun continues to fascinate scientists and enthusiasts alike, offering a window into the intricacies of celestial mechanics. While its reclassification as a dwarf planet sparked discussion and reshaped our understanding of planetary bodies, later discoveries about its orbit have reignited interest in its role within the solar system. Neil deGrasse Tyson and Michio Kaku, two prominent voices in astronomy, have raised concerns about a possible collision between Pluto and Neptune, shedding light on the complex forces at play in our celestial neighborhood. Their warnings emphasize the importance of understanding the gravitational interactions and orbital mechanics that govern the movements of celestial bodies. Pluto's orbit, characterized by its eccentricity and steep inclination, defies conventional assumptions and challenges our perspective on planetary motion. Unlike the nearly circular orbits of its neighboring planets, Pluto's path follows a unique course, crossing with Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, especially Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over many years, despite the tumultuous nature of its path. Numerical simulations and theoretical models play an essential role in predicting the future behaviors of celestial bodies and understanding the complex interactions between planets. These simulations show that, while Pluto's orbit is chaotic over millennia, it remains relatively stable within the broader context of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as proposed by astrophysicists Neil deGrasse Tyson and Michio Kaku, underscores the ongoing uncertainties and unpredictability in planetary dynamics. While such an event remains speculative and highly unlikely in the near term, the gravitational dance between Pluto and Neptune highlights the delicate balance of forces that govern celestial bodies within our solar system. Beyond its scientific significance, the study of Pluto offers practical insights for future space exploration missions. NASA's New Horizons spacecraft, launched in 2006, provided remarkable images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed stunning details of Pluto's surface features, including mountains of water ice and vast fields of frozen nitrogen, enhancing our understanding of the geological processes shaping the distant dwarf planet. The success of New Horizons mission highlighted the technological advancements and collaborative efforts required for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of celestial bodies, and the environmental conditions present in the outer regions of the solar system. These discoveries have implications for future missions to explore other dwarf planets and trans-Neptunian objects, helping us understand planetary formation and evolution. Pluto's status as a dwarf planet has also sparked discussions about the criteria used to classify celestial bodies within the solar system. The debate over planetary classification reflects broader questions about scientific categorization systems and the evolving nature of astronomical knowledge. While Pluto meets several criteria for planetary status, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet underscores the diversity of celestial bodies beyond the traditional 8 planets. Studying Pluto's orbit expands our knowledge of celestial mechanics and planetary dynamics to the outer reaches of the solar system. By examining the interactions between Pluto, Neptune, and other celestial bodies, scientists can gain further insights into the formation and evolution of planetary systems. These insights are crucial for developing theories about the origins of our solar system and understanding the processes that shape planetary bodies over billions of years. Pluto's discovery and subsequent study have contributed to our understanding of planetary migration and the development of the Kuiper Belt, a region beyond Neptune populated by small icy bodies. Studying Pluto's orbit provides clues about the gravitational interactions that may have influenced the formation of planets during the early stages of the solar system's development. Understanding the intricacies of celestial mechanics can also inform future space exploration missions, including the search for habitable worlds beyond our solar system. By studying the movements of distant celestial bodies, astronomers can identify potential targets for future exploration and assess the feasibility of traveling to other star systems. The potential impact of a Pluto-Neptune collision, while highly unlikely, serves as a reminder of the dynamic nature of the universe and the unpredictability of large-scale events. As we continue to explore the outer reaches of the solar system and beyond, the study of planetary orbits and celestial mechanics will remain a central focus for astronomers and space agencies alike. Pluto's orbit, which deviates significantly from the paths of other planets, offers valuable lessons about the complexities of planetary motion. The stability of its orbit over long timescales, despite its unpredictability, provides important insights into the balance of forces that govern the movements of celestial bodies. In a sense, the ongoing study of Pluto's orbit and its potential interactions with Neptune mirrors the broader challenges of understanding the universe at large. With each new discovery and each theoretical model, we continue to refine our knowledge of the cosmos, uncovering the mysteries of distant worlds. The ongoing study of Pluto's orbit, as well as its interactions with Neptune, provides valuable insights into how our solar system functions on a larger scale. While a potential collision between Pluto and Neptune remains highly speculative, the discussion about their gravitational relationship sheds light on the dynamics that govern the motion of celestial bodies. This is especially significant as it helps astronomers develop more advanced models of how planets and other objects interact, both in our solar system and in systems around other stars. One important consideration in these studies is the role of resonance. Pluto and Neptune have what is known as a 3:2 orbital resonance, meaning that for every 3 orbits that Pluto completes, Neptune completes 2. This resonance is what prevents the two from colliding, as their orbits are synchronized in such a way that their paths never actually cross, despite their close proximity at certain points in their respective journeys around the Sun. The gravitational interaction between these two planets is such that it maintains a stable balance, even though their orbits intersect. This resonance is an example of how complex gravitational interactions can stabilize seemingly chaotic orbits over long periods of time. The study of these interactions allows astronomers to refine their understanding of gravitational dynamics, which can be applied to other systems, particularly those involving exoplanets. For example, the study of planetary resonances in distant solar systems may reveal new information about the stability of these systems and the possibility of life-supporting planets in orbits that might otherwise seem unstable. The potential impact of Pluto and Neptune's collision also raises questions about the long-term future of our solar system. While such a collision is unlikely in the near future, it highlights the dynamic nature of the cosmos. The solar system is not a static place. Its planets and other objects continue to evolve due to gravitational forces, with planets sometimes moving closer or farther from the Sun over immense periods of time. The movement of these bodies could eventually lead to the rearrangement of the solar system, potentially altering the orbits of the planets and their moons. Such changes could have profound implications for life on Earth, though this is many billions of years away. Additionally, the potential for large-scale events like a Pluto-Neptune collision underscores the need for continued monitoring and research in space science. As our technology improves, we will be able to observe distant objects in greater detail, enabling us to predict future events with more accuracy. This research not only helps us understand the mechanics of our own solar system, but also prepares us for the exploration of other star systems. By learning more about how objects like Pluto behave, we are better equipped to understand and explore distant worlds, whether by robotic missions or human exploration. In conclusion, while the possibility of a Pluto-Neptune collision remains unlikely, the research and ongoing observation of Pluto's orbit provide crucial insights into the workings of our solar system. They reveal the complexity of celestial dynamics and help scientists refine their predictions for future planetary movements. These studies also have broader implications for the search for habitable planets in other systems, showing the importance of understanding the stability of orbits and the long-term behavior of planetary bodies. With each new discovery, we expand our knowledge of the universe, moving closer to unraveling its many mysteries.